everyone. I'm going to present kind of a review, so it will be biased and incomplete as all reviews, I guess. And so please do not hesitate for those specialists who are in the room to intervene if there's some errors or something like this. So I've been asked to do some review about modeling transport processes in stellar radiative interiors. And so the first question I had was, which kind of stellar processes do we want to talk about? What are we talking about? Because, of course, in order to include them in stellar evolution modeling, because this is what we are going to talk about, and stellar evolution modeling, as you all know, up to now, is still stuck in 1D. So this includes lots of very strong constraints on which processes we can afford to include in stellar evolution modeling. So the transport processes I will be talking about are processes that will transport either angular momentum or nucleides, noticing that most of them are transporting both angular momentum and nucleides. So here I have put a list, if I can unfold me from my bracelet, sorry. I'm stuck. Okay. So here I've put a list. So you have transport angular momentum, everything which is rotation-induced processes, and I will come to it just in a few moments. Then you have the winds, and mass loss is very much forgotten in this kind of things, but winds are important to transport angular momentum and nucleides. You have internal gravity waves, I will come to this later, magnetic fields, and for the transport of nuclei, you have other types of transport processes that are important, and I would say even mandatory in some cases. And these are the double diffusive convection. You already heard about this this morning in the talk of Isabelle Baraf, and atomic diffusion. So I will start my talk browsing through these different transport processes, just describing them and describing how they are implemented in stellar evolution codes. And then I will present you some bias overview of the results that are obtained with models that include this kind of processes. So as you see, these processes, most of them are strongly related to rotation. It's not the case of all of them, but for transport of angular momentum, they are mainly, for sure, related to the fact that the star rotates, and in particular, they are particularly sensitive to the fact that the star rotates differentially. The radiative regions rotate differentially. So let's start with the transport of angular momentum. Here is a view graph that was published in Decrescent 2009, made by Stéphane Matisse, and just summarizing a bit for you the different scales of the transport processes, in particular the hydrodynamical transport processes. And you have here in the x-axis the angular resolution, and here the time scales. And what you see is that actually we would like to do everything in a row. That's to say the global evolution of a star over its entire lifetime. Unfortunately, up to now, it's not yet possible, even though there are many efforts in the international community to go to this direction. And so we are stuck with this kind of scheme where you have the theoretical hypothesis that can look at lots of scales and all the time scales. But then, if you want to do secular evolution and so go through integrated evolution, you need to restrict yourself to secular transport and to some prescriptions that will be derived from theory. Global numerical simulations allow you to access larger angular resolution, more precise things, but of course you cannot evolve them up to now to long evolutionary timescales. So to start for transport of angular momentum, it's what is called and what you will hear to be mentioned as rotation-induced mixing. And you have first the meridional circulation, which was first devised or introduced in the early 1920s, but then was reformulated by Bousset, Zahn, and then Riotor. As a circulation that operates in radiative regions due to the it's a wind-driven circulation in the sense that it's induced by the gain and losses of angular momentum in this region. And here you have a small cartoon showing you this kind of circulations that can be either clockwise. So here you have an inward transport of angular momentum, or in the other way around, and you will have an extraction of angular momentum. And then you have also a bunch of family, and I will not enter into the details of hydrodynamical instabilities that are induced by differential rotation, and that triggering turbulent transport will allow the angular momentum to evolve also through these hydrodynamical instabilities. So there are essentially baroclinic instabilities and double diffusive instabilities. And then you have the shear instability, which to which lots of work has been devoted, and particularly the work by Zahn. And so this instability appears because you have small viscosity in stellar interiors. So you always have a scale to which the horizontal shear becomes turbulent. And there's a formalism that is available to us, which relies on the hypothesis of cellular rotation, meaning that you assume that you have a stable stratification in radiative interiors, which is not a very strong assumption. But then what you assume is that you have an anisotropic transport, of matter, meaning that the horizontal shear is much larger than the vertical one. And this will create a cellular rotation. This is the strongest hypothesis of this theory. But doing so, you go from a 2D or 3D problem, which is a retroacting problem, to a 1.5D problem, which you can actually reformulate in order to describe it as something that you can input in stellar evolution codes, which are only 1D, so which is what we are looking for. So this is one of the formalisms. Moving now to winds. The winds are quite important because the mass loss triggers angular momentum loss also and transport. So the physical mechanisms for the winds are different according to the initial mass and to the stellar evolution phase. And so there are different prescriptions for these winds that will create transport being formalized as torques, which is the case for low mass stars or solar type stars, which are undergoing magnetized stellar winds or disk wings also during the pre-main sequence evolution. And here you have the kind of formula that is available to us, where you have a dependency, you have some parameters, here the K and M, which are calibrated on simulations. In this case, this is from Matt et al. 2012. And then it depends on the rotation rate of the star, on the radius of the star, and on the mass loss also, and magnetic configuration. So you see that you need to have already a good knowledge of your star in order to be able to have a good model for the wind, but this will for sure drive a part of the evolution of the angular momentum of your star from the pre-main sequence to the age of the sun if it's a solar type star. For more massive stars, even though these stars are beyond the scope of the studies that have been done with CoRoT and Kepler, for the very massive ones, you also have the fact that the radiative winds will induce mass and angular momentum losses. And actually, rotation in these stars will modify the mass loss through here, as you see, the Eddington factor and the modification of the total gravity of the star. And so you will have a retraction of the wind on the transport of angular momentum, and it's actually crucial because in these very massive stars, the winds and the mass loss are a real driver for stellar evolution, which is not really the case for main sequence solar type stars or intermediate mass stars. So when you combine the treatment of the rotational mixing that I showed you and the winds, you end up with something which is a bit self-consistent or coherent. And we are left with perturbative approach because we want to implement this in 1D stellar evolution code. And there we have several, actually 2 formalisms that exist. And one is using a purely diffusive approach, which is here, has been developed first by Endal and Sofia and implemented in several stellar evolution codes with a great success. And the other one developed by Jean-Paul Zahn and Meder and Zahn, under the cellular rotation hypothesis, in which this meridional circulation I talked to you about just before is modeled as an advective process and not as a diffusion process anymore. So as you see in these equations, you have these new here quantities, which are diffusivities associated to any hydrodynamical instability. So in the case of the diffusive formalism, this new includes all the hydrodynamical instabilities that you would think of that would be capable of transporting angular momentum. In the formalism of Zahn, it's only shear turbulence. And then for sure, of course, you add the wind torque, which will exert some more constraint on the angular momentum and drive it at some phases. So this is how we treat the angular momentum with rotation and winds. As I told you, there are other processes that will also lead the transport of angular momentum. There are the internal gravity waves. So these waves, they propagate, they are excited at the base of, at the interface of convective zones, at convective zones edges. The excitation mechanism is yet under study, but the main mechanisms are turbulent motions and internal stresses, Reynolds stresses. They propagate in a highly stratified medium along a favored direction. And normally they will conserve angular momentum if they are not dissipated. But we expect that in differentially rotating media, there will be a filtering of prograde and retrograde waves that will lead to an uneven balance between these two families of waves, and then you will have either a net extraction of angular momentum or a deposition of angular momentum. So you will have these kind of things. These internal gravity waves, we have some analytical and theoretical work to include them in stellar evolution codes. I will show you in the next slide. But they have been found in numerical simulations in different evolutionary stages. And Sacha Brun will talk to you about, will present some results in solar-type stars. And here is an example where you have the convective envelope and these waves that are generated at the edge of this convective envelope and propagate inside the radiative zone. And here you have another example with the propagation of the waves. I'm sorry, maybe you don't see them very much, but here it's down this convective shell, and here is in the upper part of the convective shell. And this has been found here for an intermediate mass star and here for a massive star during moments of the evolution where you have off-center ignition of nuclear reaction. So these internal gravity waves, we want to include them also to treat self-consistently the transport of angular momentum, and this is done in stellar evolution code through a formalism that was first proposed by Goldreich and Kumar, and it's done through the wave's luminosity that you see here appearing in this equation for angular momentum, again in 1D. So it's, again, the same kind of perturbational approach. Then I will turn to magnetic fields. So magnetic fields are actually very badly represented in stellar evolution codes for the transport of angular momentum, even though they should be very important. So they affect the transport of angular momentum and nucleides, and this is done via magneto-hydrodynamical instabilities, and I will just come back to the Taylor instability in one slide. And then via the magnetic torques that are introduced by the Lorentz couple. And here you have, again, this very same equation for the transport of angular momentum with the magnetic torque here entering this equation. There's another way to transport, not only the Lorentz torque. I was talking about the hydrodynamical instabilities. And the one that has been the most studied is the Taylor-Sprott instability. So the magnetic fields in stellar stably stratified interiors can be unstable to axisymmetric perturbations. And the first instability that develops is the Taylor-Sprott one. It's supposed to produce a poloidal field, which is entertained by a dynamo process, and this should retract and decrease the differential rotation. So this will impact in an important way the transport of angular momentum, but this instability, even though the formalism that is included in some stellar evolution codes, it has been compromised by analytical 3D and 3D simulations, and also by the confrontation to observations in the case of massive stars. And up to now, there are not that many people still working on these kind of processes. So to summarize the transport of angular momentum, you have this, again, this view graph from Stefan Matisse, and you have rotational mixing of type 1, which is only meridional circulation and turbulent transport, acting on the transport of angular momentum and distribution of chemical elements. And then you have this type 2, where you add internal gravity waves or magnetic field, or both, but both have never been done, in order to treat the whole loop of transport of angular momentum. Let's move now to the transport of nucleides. So for nucleides, the very same processes I just described are applying also. They also transport nucleides, but there are other processes, more fundamental ones. Atomic diffusion is one. It's mainly due to the, you can have stratification inside a radiative zone. It's that where you have a competition between the gravitational settling and the radiative levitation. And here you have an illustration of this. And so this process is mainly important in A-type stars. In the sun, we also know that it's important to include atomic diffusion, but it's really, it is very strong when there's no competing transport processes that hinders it. And here you have the description of the evolution of a concentration of nuclide, and you see here that you have the atomic diffusion and the competing processes, which are the ones I just presented before. Another transport of nucleides that you have is the double diffusive instability, the so-called thermohaline instability. It develops in the astrophysical context in regions where you have a stably stratified entropy and an unstable stratified chemical composition. And in particular, this occurs in red giant stars where you have this helium-3 reaction. And it also can happen in A-type stars where you have these heavy elements concentrations due to atomic diffusion. We have several formalisms available in the form of a diffusion coefficient for this instability. And the predictions of the formalisms can vary a lot. And we will have an efficiency of this kind of process, which is not yet calibrated, I would say. I will go quickly through the winds that will also trigger angular momentum, nucleides evolution, transport, in particular in A-type stars where you have a weak mass loss that will create an advection term in the transport equation for species. And again, in massive stars, the modification of the turbulent transport will also affect the transport of nuclides. And in the end, the rotation, where you have a purely diffusive equation and where both meridional circulation and hydrodynamical instabilities can be modeled as diffusion coefficients. So you have simple equations to be solved in stellar evolution codes. So I will move now for the rest of my talk to some applications of this kind of modeling for you to have a grasp on how does it affect the evolution of stars and how does it affect how well or badly we understand the angular momentum evolution in solar type stars. I will first start with the effects of rotation on the stellar structure and evolution. Here you have two view graphs. Here is type 1 rotational mixing, so that's meaning meridional circulation and hydrodynamical instabilities, shear instability. Evolution integrated for stars from 1 solar mass to, I think this is a 5 solar mass star. And you have the standard, which is dotted lines, and rotating models with solid lines. And you see that the evolutionary tracks are affected by the rotation. You also have, when you include magnetic fields, which means type 2 rotational mixing, using this Taylor-Sprout instability, you also have, here is for an illustration for massive stars, a very different evolutionary path on the main sequence, the red being the path for the magnetic and rotating star, and here the dotted line is the standard, and here is only rotation. Globally, what you should expect when you include rotation and the other processes that can transport angular momentum and chemicals, you will result, all the results of all the codes that include these processes are that the lifetimes of rotating models on the main sequence are longer, essentially because of the mixing of hydrogen of the core, which, so the hydrogen burning phase will be longer, and the cores are larger when you have rotation. And so this will induce a change in the lifetimes, also a change in the structure. Radii may change a bit. And also, for sure, the size of the cores will change. The mass of the helium cores of this is wrong, it's not helium, but it's hydrogen cores, will change when rotation is accounted for. Moving to abundance patterns, here you have the results that are obtained when you put atomic diffusion to explain A-type stars, and this is Sirius A, and you have different models including either winds and atomic diffusion or turbulent mixing and atomic diffusion, and you see that you really need these kind of processes to, for instance, explain the abundance patterns on Sirius A, and it's quite successful. Now, if you move to intermediate mass stars in what we call the range of between 1.3 and 2 solar masses at solar metallicity, you see that including transport associated with rotation, you also have a very good reproduction of the lithium abundance in the subgiant branch, whereas you can't reproduce this distribution at all with standard stellar evolution models. Again, the internal gravity waves, if you include them in models, it has not been done that much up to now because it's quite tricky to introduce and the excitation mechanisms and formalism are not completely settled. But here, this dashed line are the predictions from evolutionary models of the evolution of lithium as a function of time. And you see that you obtain a very strong depletion of lithium. But when you include internal gravity waves, the effect of turbulent transport is counterbalanced, and then you have these solid track lines that reproduce better the evolution of lithium in clusters of different ages. And thermohaline mixing, this double diffusive mixing, also using a very maximized prescriptions, allow to explain some abundance anomalies here in red giant stars. Here you have the luminosity, so this is the tip of the red giant, here the base, and you have here the carbon isotopic ratio that is otherwise not at all reproduced by standard stellar evolution models. If we go now to the rotational evolution, I will browse through rapidly. You will see that more or less using the talks and the prescriptions that I showed you, we have not a bad understanding of the evolution of the angular momentum during the pre-main sequence up to the age of the sun on the surface. These are data in open clusters. Here you have the age and the rotation rates, and you see that we more or less are able to reproduce these large variations. But when you get to the sun, here you all know that we're stuck with a problem. This is the inversion of the helioseismology, and you see that you have more or less a very flat profile in the interior of the sun with a tantalizing going up again of the rotation in the core from the candidate G modes that were obtained by Raphael in this plot. If you use normal stellar evolution or type 1 rotational mixing, you have these kind of plots. Here you have the structure of the star. So this is the surface, this is the core. And here you have the same data that are reproduced. And in order to fit, and you don't fit them at all, but to have a gradient of rotation between the core and the surface that is more or less the same that the one we think should be in the sun, we need to assume that the sun has always been a very slow rotator with the same rotation that it has from present, but that it has been holding this very same rotation from its birth, which is completely unrealistic. So type 1 rotational mixing doesn't work, but type 2 rotational mixing, so if you, in addition to turbulence and meridional circulation, include angular momentum transport by internal gravity waves or magnetic fields, it seems that they will do the trick of flattening out the profile of angular velocity in the sun. And here you have the example of magnetic models, and here of models with internal gravity waves, and the sun, the edge of the sun is here, the red line, and here the blue line, and you see that you end up with a very flat profile, which is in much better agreement with observations. When you move, this is another mass, but I will skip it. And so now we move to the new era that has been opened really by asteroseismology, because up to now we were left with no constraints apart from some V sin I and abundance anomalies at the surface for red giants, spectroscopy. So we could do whatever we wanted concerning the rotation inside stars. No one was telling us that it was wrong. But then asteroseismology came and everything collapsed. because it doesn't work anymore at all. Here you have some results that you might have all seen already on the evolution of the contrast between the envelope and the core rotation velocity in subgiant stars, where you have an increase of the differential rotation inside the star during the subgiant branch, and then you have again an inverse evolution when you go from the red giant to the clump. And when trying to reconstruct the angular rotation profile as Sébastien de Heuvel's did in this star, what you end up with is a differential rotation with a contrast of about a factor of 4 between the core and the envelope. So this is very nice and beautiful constraint, but when you go to our stellar evolution models, it doesn't work at all, and not by a small factor, by 2 orders or 3 orders of magnitude. Here you have profiles that are obtained with the transport rotational transport of type 1, meaning only meridional circulation and turbulence, and you see that the contrast between the envelope and the core is of 2 or 3 orders of magnitude, which is completely off compared to what is observed. So we need another mechanism in order to transport angular momentum very efficiently during this red giant branch phase. And this we don't know. Some attempts have been done, in particular by Patrick Egenberger here in 2012, where he shows that adding an ad hoc viscosity, and it's a transport which is not negligible because it will be equivalent to a diffusion coefficient of 10 to the power of 4 centimeters square per second, you are able to flatten out to have a very efficient transport of angular momentum and to have a better agreement with pulsations. So I will stop here with my conclusions, hoping that I didn't just bury you with too many questions and things like this, but the important point is that transport processes in radiative zones are there. They should be introduced in stellar evolution codes. They are now routine in most of the modern stellar evolution codes. They suffer many limitations, not only one, but many. In particular, everything I showed you does not include any coupling or interaction between processes, and this is a very big flaw. We don't know yet how to deal with magnetic fields correctly. Internal gravity waves, it's starting to emerge, and Sasha will show you new results just now. The efficiency of thermohaline mixing is also a bit discussed. We need to understand the impact of interplay between atomic diffusion and the other transport processes on the pulsational behavior of A-type stars. And really, thanks to asteroseismology, we entered a complete new era on our understanding of these quite amazing stars on this red giant branch. And we really need to understand the integrated angular momentum evolution self-consistently to understand what you observe in red giants. So lots of work to do. Thank you.
Questions? 1 or 2?
Yep. Just right at the end, when you are puzzled about the rotational profile in giants, red giants, why don't you call on a magnetic field? It seems to be obvious. Seems to be obvious in the solar case to produce uniform rotation.
Yeah.
And people only ignore it because it's difficult.
No, well, yeah, actually it's been ignored for long, and it's been the carpet under which we've put all our problems, saying that it might be magnetic fields. There are now some observations of magnetic fields in red giant stars. It's very often very small, very weak magnetic fields in these stars.
You don't need a strong magnetic field to transport angular momentum over a reasonable period of time.
Yeah.
Right. So it's done, and it doesn't have to be at the surface either.
Yeah, that's what I'm saying, that we really need to understand what's happening with magnetic fields, because in the end we had some hope with the Taylor-Sponson ability, but it's been really compromised, and up to now we're left with nothing. So I think it's still a very good candidate.
And my other comment was, you are spherically averaging everything.
Yeah.
A very long time ago, I think it was 1954, Leon Mestel showed that the circulation produced by rotation produces an angular-dependent chemical composition profile which acts in the opposite way and can stop the circulation. Another way of saying that is that a latitudinal composition gradient, right, can inhibit otherwise things like symmetric paracrinic instability can be stabilized by that.
Okay, one quick question over here.
Just kind of a brief comment in kind of related to what Ian just said. One of the challenges here is that the core to surface contrast in these stars is significant. And therefore, as a result, if you had a very, very strong organized magnetic field in the interior, you'd expect much less differential rotation than you observe. So we have kind of a complicated problem where the coupling is both too strong and too weak.
Too weak, yeah.
Okay, let's thank the speaker again.